Okay, this is section 19.4, spontaneity of redox reactions under standard state conditions. Now, if you recall back in chapter 18, we talked about spontaneity from a couple different perspectives. We looked at it from the perspective of entropy, right? That if the total entropy increases during a process, that means that the process is spontaneous. But we also said that it was perhaps more convenient to use energy units than entropy units. So what we did was we said that there's something called the Gibbs free energy change, delta G, and that if delta G was negative, that would be a spontaneous process. Well, electrochemical reactions involve the transfer of electrons, and some of those reactions are spontaneous and other ones are not. So there is a connection between our discussion of electrical energy and that of thermodynamics or spontaneity. So let's begin. I'm going to write down pieces of information that are be useful for us to use as we move along and start talking about spontaneity. And so the first thing I'm going to do is I'm going to say that if we want to calculate the amount of electrical energy during a process, what we do is we take the number of volts and we multiply that by the number of coulombs in the process. And that product is in joules. Okay? Let me put a couple. I'm going to write E for voltage, Q for coulombs, that's charge, right? Q is charge. And that would be equal to the number of joules. Okay? Now typically the abbreviation for volts, these are the units, is volts. And then for coulombs is a capital C. So 1 volt coulomb, right, volt times coulomb, would equal 1 joule. All right? I'm also going to claim that if electrons are passing through an electrical circuit, so maybe you're in a galvanic cell, you're looking at a galvanic cell like we looked at in the previous sections, the total charge that is transferred through the circuit is equal to the number of moles of electrons times something called a Faraday, or Faraday's constant. And a Faraday is nothing more than a conversion between coulombs and moles. And it's 96,000, approximately 96,500 coulombs per mole of electrons. C for coulombs, that's the amount of electrical charge in coulombs divided by mole. Now that number comes about because 1 mole of electrons is Avogadro's number, right? 6.022 times 10 to the 23rd electrons. Well, it turns out 1 coulomb is approximately 6.25 times 10 to the 18th electrons. So this Faraday is nothing more than the conversion between coulombs and moles. There are 96,000 approximately, 96,500 coulombs for every mole, because if you took Avogadro's number and you divided that by the definition of a coulomb, 6.25 times 10 to the 18th, sorry, that's an 18, you would get that number, 96,500. Okay? Now, we can also write it another way. We can say that 1 Faraday is 96,500 joules per volts, right? Joules per volts. Now, where did I get that? Joules divided by volts is equal to coulombs, right? So if it's coulombs, then we could make that joules per volt per mole electrons. Okay? So there's our number right there. Now I'm going to state the following, which is that we're going to claim, this is a claim, that the maximum amount of work, and this is electrical work, is equal, so I'm going to say electrical, is equal to minus N times F times E cell. And here's an important equation. This tells us that the maximum amount of electrical work that we can pull out of an electrical circuit like a galvanic cell is equal, or proportional I should say, to the cell potential. And so this equation, F and N, again, N is the number of moles of electrons. F is this Faraday's constant. And then E cell, of course, is the cell potential, right? So we can measure cell potential, right? We learned that it is possible with a voltmeter or a potentiometer. We can measure the cell potential. So you could measure the cell potential, and that right there would tell you how much work, how much energy you could pull out of a galvanic cell. That's really cool. So now the next thing is to come back to chapter 18 briefly, because that's really what we're doing here. We're connecting chapter 18 to 19. Is that if you recall, the Gibbs free energy change, delta G, that's also the maximum amount of work that can be extracted out of any kind of chemical system. So that would include electrical systems like galvanic cells. So that means we can connect the two. Delta G is equal to minus NF E cell. That's an important relationship right there. It says the Gibbs free energy change is directly proportional to the cell potential. And we can equate them by using this equation. If we're under, so this is under standard or non-standard conditions, but if we're under standard conditions, meaning 298 Kelvin typically, and the solute molecules that are electrically active are at 1 molar, and any gases that are electrically active are at 1 atmosphere, we can put this equation into standard form. So the Gibbs free energy change under standard conditions is minus F E cell under standard conditions. So remember that what that means is that we can use table 19.1 values, right? The standard reduction potentials can be used, right? Right? According to that equation where we said that E cell under standard conditions is E cathode under standard conditions minus E anode under standard conditions. So there's another important relationship right there. Okay. Now, we can also connect it to the equilibrium constant we learned in chapter 18. So this is chapter 18, of course, as was this, that the standard Gibbs free energy change is related to the equilibrium constant, right? Oops, sorry. Not in that way, it's not. ln of k, right? I'll put this in parentheses. Okay, oops, sorry. I skipped ahead a step. Sometimes I do that. My mistake, sorry. Minus RT ln k. There we go. Right? We said the standard Gibbs free energy change is related to the equilibrium constant by minus RT ln k. But now we have this situation over here. So now we can say that minus RT ln k, so we're combining these two, right, is equal to minus NF E cell under standard conditions. Now that's not a particularly pretty looking form of it. So typically what people do is they modify it to make it a little more useful. And so the way I'm going to do that is I'm going to isolate E cell. So I'm going to divide both sides by minus RT, by minus NF. Okay, there we go. So if you divide by minus NF, they cancel. The negatives cancel, and you've got RT over NF. I'm just going to write it out a little differently here on the left. Okay, so R times T times ln K divided by N divided by F, but I'm just going to write it in that form just to make it look prettier. Okay, and there you go. That's our sort of one of the conclusions here, which says that the standard cell potential is related to the equilibrium constant according to this equation here. Isn't that interesting? So if you somehow measure the equilibrium constant, that can give you the cell potential. Or of course you could do it vice versa, right? You could find the equilibrium constant from the cell potential if you wanted to do it that way as well. Okay? Now I'll point out that some of these values that are in this equation, this one right here, are constants, right? F is a constant. That's Faraday's constant, 96,500 coulombs per mole. R is a constant. In energy units, it's 8.314 joules per kmol. So what I'm going to do is I'm going to say, suppose we're under standard conditions and the temperature is 25 degrees C, which of course is 298 Kelvin. We could modify this equation a little bit, and here's what I'm going to do. I'm going to put in the value of R, which is 8.314 joules per kmol. I'm going to put in the value of T, which is 298 Kelvin. And I'm going to put in the value of F. I'm going to go ahead and do a couple extra sig figs, not 96,500, but 96,485. Doesn't really matter. It's not going to make a big difference, but I'll use some more sig figs. And that was coulombs per mole. Okay? So those are constants, essentially, for this setup. So what does that mean? It means that if you take RT and divide it by F, here's what you get. 8.314 joules per kmol. So there's R. 298 Kelvin, there's T. And then divide that by 96,485 coulombs per mole. Now let's get rid of some units here. The moles cancel, right? And the kelvins cancel. So you've got joules per coulomb. So it's some number in the units of joules per coulomb. Let's figure out what that number is. Yep, that's something we should be able to calculate, right? Oops, there we go. All right, so RT over F. So R is 8.314. T is 298. F is 96,485, and you get 0.0257, I'll round it to 0.0257. Now the thing about the units is that a joule per coulomb, coming back to our units over here, up at the beginning, if you take joules over here and you divide it by coulombs, 1 volt is the same as a joule per coulomb. Okay, so now I can come back all the way over here, if we can find it. Let me put another, it's just right underneath here. This would be 0.0257 volts. Isn't that interesting? So it comes out to volts. RT over F is in volts. So now what we have is 0.0257 in the unit of volts divided by N, right? Because we still have this N down here. We did RT over F, but we still have the N. So that's in volts times ln K. I guess I put that in parentheses, so I'll do it again. That would be equal to the standard cell potential. So this is a little easier to calculate. Instead of actually putting in the value of R, the value of T, and the value of F every time, we can just use that value 0.0257 in the unit of volts. Remember, The K doesn't have units anyways, so ln of K doesn't have any units. And remember, this is the number of moles of electrons transferred in the chemical reaction. Okay, remember, we're talking about redox reactions, so electrons are transferring through. Now, I'm going to point out that for historical reasons, having to do with technology, really, people didn't have calculators in the past, they had books instead of calculators. It was easier to have this in log, L-O-G. So we're going to change it to log base 10. Just like you do for pH, you have log base 10. We're going to do this in log base 10. Oops, sorry. It's a change of base calculation. So if I change this to base 10 of K, what I have to do is I have to multiply this by the natural log of the new base, which is 10. The natural log of 10 is approximately 2.303. So if you take this number here, 0.0257, and you multiply it by 2.303, you get a modified number. It comes out to approximately 0.0592. So you will more likely see this, instead of seeing it in the natural log form, as it is over here, you're more likely to see this number, 0592 volts, over N times log base 10 of K. That's equal to the standard cell potential. And that form is, as I said, it's just, you're going to see that more often. Both can be used to do the calculations. And now the fact that we have calculators, we have electronic calculators that we can do natural log calculation just as easily as log base 10, means that we don't have to use this form. We could use this form up here if we wanted to, but it doesn't really matter. We can use either one. They'll give us the same answer. If you want to just test that, just make up a couple numbers. For n, make 1, and then for k, make it 2. Don't make it 1 because the log of 1 is 0. But if you put in a value like 2 for k and a value of 1 for n, just to make it simple, and calculate the standard cell potential for either this equation or this one, you'll get the same answer. So the one thing I would say, notice in this discussion that we're wrapping up here, it's a lot of new definitions and such. The important ones, I would claim, are this one right here, the maximum electrical work. But the maximum electrical work, of course, is the standard free energy, or the free energy change. So those two equations right there are the ones that are very, very useful. And then if we want to connect free energy change to the equilibrium constant, we did that back in chapter 18, so that's not really this topic here, but it's connected, right? So it's really those two up here, and then this last one over here, this final result over here. 0.0592 volts over N times the log base 10 of K is equal to the standard cell potential. Okay, and there you go. Now it's just a matter of just using those equations to do the calculations.